Good afternoon. This is Professor Shannon Gracie from Miracosta College, and we're working out of Blitzer's Introductory and Intermediate Algebra for College Students text. Today we'll be covering section 11.3, which is quadratic functions and their graphs. And this one's going to take a little while, so you might want to make sure you've got enough time to complete this lecture. We've got a lot going on in here. So we'll be learning how to graph parabolas. Actually, sorry, my bad. We've got a typo here. We learn how to graph parabolas in that first format and then also in this format here. So we'll be working on both of them. So we also will determine a quadratic function's minimum or maximum value. We can use that to solve application problems that are quadratic in form. So here we go. Let's go ahead and we'll do this form up together because I'm going to introduce some concepts of symmetry that you might not be used to aid in our lesson today. So here we go. Let's take a look at, this is just, you've graphed this one before, you probably have an idea what it looks like, but this will kind of give us the basis for understanding more complicated quadratic functions. What I'm going to do for my x values, we have this one here has its vertex, its lowest value is located at the origin. So it turns out that it has symmetry across the, or about the y-axis or the function axis. So this is what I'm going to do. I'm going to pair up these numbers here. Now we don't always know where the symmetry is going to be before we find the vertex, but in this case we know it's going to be on that y-axis. I just wanted to show you how you can use symmetry. All right, so we're going to start, I know this seems a little backwards, but we're going to start here. F at 0 is equal to 0 squared, which is 0. So we get an ordered pair of 0, 0. And actually this one should say x comma f at x, which is, just function notation instead of equation notation. Okay, so we have an ordered pair at 0, 0, right? We're gonna use the regular scale here. So this is x, this is f at x, and then remember these axes, this grid goes plus or minus 10 if you use 1 unit per square. So now if I plot 0, 0 right here, it turns out we've got what's called a line of symmetry. A line of symmetry. Let's see what'll show up the nicest here. Maybe the green. So the line of symmetry, I don't know if you can see that green very well. Well, let's try the purple. The line of symmetry, it goes at the x coordinate of the either minimum value or maximum value. So what that means is if you were to fold the parabola, it would fold on that line. So thinking about that, let's check out these other values. So coming up here, f at -3 is equal to -3 squared, which is 9. So the ordered pair that we'll get is -3 positive 9, my bad. So let's take a look at it. You got to figure out how far to the left or right you moved away from your axis of symmetry, that purple dashed line that we did. So if I go 1, 2, 3, do you see that I'm 3 to the left? So what that means, it's really kind of cool. You get 2 for 1 points. You're going to have at the same height, the same left-right distance away from the axis of symmetry, you're going to have another value at that same y value. So this is 1, 2, 3 away from the axis of symmetry. So we'll go 1, 2, 3 in the other direction, and we get another ordered pair. So at +3, 9, we get another ordered pair. So we kind of got a 2-for-1 special on our points. And then if you want verification, right, you can always evaluate the function at that value. But I'm going to say we will get f of 3 is positive 9 using symmetry. So we get the ordered pair 3, 9. All right, similarly, if we work out f at -1, you get -1 squared, which is 1. So we get the ordered pair -1, 1. So when we graph that, we're here, -1 to the left and 1 up. So you tell me, where do I go? Good, if I go 1 to the right, I'm at the line of symmetry, and if I go 1 more to the right, I'm the same left-right distance away from that axis of symmetry. So now I've got my 5 ordered pairs. This one we got using symmetry. This one we worked out. And this here is the vertex. And that vertex is located at 0, 0. So since we have a positive x squared, so there's really a 1x squared, so the coefficient of the x squared is positive, what happens is that your parabola opens upwards. And so you draw it with a smooth curve, and there you go. You've got your graph. Okay. So, doing the next one in a similar way, we can go ahead and we can say, okay, might as well use the same values. So where's my vertex going to be? Good, it's going to be at the origin again. So f at 0 will be -0 squared, which is just 0. So we get our vertex at 0, 0. And again, I'm going to call this x and f of x, and then we'll use the regular scale. So 0, 0 is our vertex. Now, we've got a -1 as the coefficient to this x squared term. So what that means is that our parabola is going to open downward. So instead of like a bowl, like we had in the last graph, we're going to have like a bowl that's inverted in this graph. And you want to just learn that and kind of memorize roughly the shapes and these properties so that you can be successful in this section. So here we go. F at -3 will be -3 squared, which is -9. So -3, -9 will be our first order pair. So 1, 2, 3 to the left of our axis of symmetry, we have an ordered pair. We have a y value, a function value at -9. So this is -3, -9. So remember that this is our axis of symmetry here, because that's where our vertex is. So where am I going to get another ordered pair using symmetry? Good, I count back to the right, 1, 2, 3 units away from the axis of symmetry. So if I go 1, 2, 3 more, I get another ordered pair. And that's +3, -9. So +3, -9, we did that using symmetry. You don't have to use symmetry. It just makes your life so much easier, all right, when you're dealing with these. Okay, and then -1. F at -1 will be -1 squared, which is -1. So we get an ordered pair at -1, -1, which is here. Where's my other ordered pair going to be? So I'm 1 away from axis of symmetry, and then I go 1 more, and bingo, I get my other ordered pair. So by symmetry, I got 1, -1 using symmetry. And then we just make our picture. All right, very good. So here we go. We're off and running on our next section. So first up, we've got quadratic functions in the form f at x equals a times the quantity x minus h squared plus k. So the graph of f at x equal to a times x minus h, the quantity squared, plus k. And then we want to say that a is not equal to 0, because otherwise we would just have a horizontal line. So this is a parabola whose vertex is the point h comma k. So h is the x-coordinate of the vertex and k is the y-coordinate of the vertex, and k will represent either the minimum or maximum value depending on if the parabola opens upward or downward. So the parabola is symmetric with respect to the line x equal to h. So whatever that x coordinate of the vertex is, you're going to have symmetry. That's where the parabola folds. If you folded it, then the parabola's lines fold on each other. If a is positive, so remember in our first graph, a was positive, and which way did the parabola open, upward or downward? Good, upwards. And if a is negative, the parabola opens downward. Okay. So here we go. There are so many so many different cases we could show you. I'm just going to draw a couple of different cases of parabolas, one that opens upward, one that opens downward, and then we'll go from there. So if we had something like this, where this is x, this is f at x. Okay, so this case is going to be when a is greater than 0, and this case over here will be when a is less than 0. A general picture. Okay, so if you have a positive parabola, it's going to open upward. Okay, let's go ahead and let's make the vertex. We can make the vertex, let's make it over here, right? So this here would be the ordered pair h comma k, called the vertex, right? And then if we go ahead and kind of draw our parabola, you're going to have symmetry. So if you think about it, it's really kind of cool. You have symmetry about this vertical line, right? And it's opening upwards because a is greater than 0. So here it's going to be about here on the intercepts. Oops. So we've got a few important values here. So these here are the X-intercepts. right? And then over here would be the y-intercept. And this here is the line x equals h, and it's called the axis of symmetry. Okay, so let's take a look at what would happen, or what it would look like if it opens downwards. So let's just say this time we've got our vertexes here. So now again, h comma k, that's our vertex, which would make our axis of symmetry look something like this. And then we would have our X-intercepts here and here. And then our y-intercept would be here. And then again, this here was our vertex at h comma k. And then again, this is x equals h, and that is our axis of symmetry. So that shows you the fold line, if you will. Right? So just a couple of basic, general examples of one parabola opening upward and the other parabola opening downward. So let's take a look at some practice problems. Now it's going to be really important because we're not using graphing calculators in this class. So it's going to be really, really important that you do these graphs by hand so that you can be successful on the exam. So here we go. We got to first determine, these are the steps for graphing. You got to determine whether the parabola is going to open upward or downward. And remember, if it opens upward when what? Good, when a is greater than 0. And it opens downward if a is less than 0. We need to also, very early on, determine the vertex of the parabola. The vertex is h comma k. You need to find any x-intercepts. That's often very useful info. By solving f at x equal to 0, so you're basically setting your function value or your y value at 0. And then you find the y-intercept by computing you're evaluating the function when x is 0. So the first one, you're plugging in 0 for the function value. The second one, you're plugging in 0 wherever you see an x. Okay, so then you want to plot everything. You want to plot the intercepts, the vertex, and then, any additional points as you deem necessary. Then you connect these points with a smooth curve. You don't want to have them like jagged. And it's shaped like a bowl or an inverted bowl. Okay, so here we go. Another thing, especially with these parabolas, I would, until you have your ordered pairs you're going to use, I would definitely wait to make your scale. So I mean, we can certainly say that this is x and this is f at x, but we don't know like how tall we need to make it or how wide we need to make it. Okay, so here we go. Ready? First of all, is this going to open upward or downward? So I guess we can say, you know, 1. So let's identify A in this case. Do you see there's just a 1 in front? So A is equal to 1. 1 is greater than 0, so it opens upward. Okay, so 2, we're finding the vertex. Okay, so here we go, and we might have wanted to do this initially. F at x equals, so that we said that there was a 1 in front of the parentheses. Now, remember that the formula was plus something at the end? So I'm just going to write this as plus -2. This mirrors exactly the format. So basically here, A was our 1. B, or my bad, not A, not B. H is the x-coordinate of the vertex, and Y is going to be the okay, so A is the 1. That's how we determined if it opened upward or downward, because it was positive, so it's going to open upward. H is the x-coordinate. It's always going to be hanging out with the x here. So it's the x-coordinate of the vertex, and then K is the y-coordinate of the vertex, and that's going to determine the max or minimum value. So in this case, it opens upward, so we'll have a minimum value. All right, so here we go. The vertex is going to be the ordered pair h comma k. Well, we just said that that's going to equal to 1 comma -2. And that's from the information that we got here. So that's our h, and our k was the -2 from above. All right. So next up, we need to find any x-intercepts. Sorry, I didn't leave very much room for work on this one. So this one, you set f of x equal to 0 and solve. So I'm going to have 0 equals x minus 1, the quantity squared, minus 2. If I add 2 to both sides, I get this. So I've got, you know, a perfect square on that side. So I square root both sides. So here, remember, I'll end up getting x minus 1 is equal to -√2, or x minus 1 is equal to +√2. So x is equal to 1 minus √2, or x is equal to 1 plus √2. And then just, you know, in order to be able to graph these, we should get approximations. So this one came to approximately 2.4, and this one came to approximately -4/10. So our actual x-intercepts are going to be 2.4, 0. well, you know, we'll write both ways. So the exact intercepts would be 1. Oh, and I'm sorry, I switched these around. I have the 1 minus here, so these are switched, these values. So 1 minus root 2 is the negative 4/10, and 1 plus root 2 was the positive 2.4. So here we'll get 1 minus root 2 comma 0 and 1 plus root 2 comma 0, but this will use the approximations when we're graphing, right? Which would be, let's come up here. Approximately negative 0.4 comma 0 and 2.4 comma 0. And the y-intercept is easier. So the y-intercept, you're going to evaluate f at 0. So notice when you evaluate f at 0, everything, you'll end up with 0 minus 1, the quantity squared, minus 2. So I plugged in 0 for wherever I saw an x. So this ends up being 1 minus 2, which is negative 1. So let's see what all we have, because we might be able to use symmetry here too. So remember that from the vertex, we found that the axis of symmetry. So the axis of symmetry I'll put it over here. Sorry, it's crowded. You might want to use another piece of paper. The axis of symmetry is x equals h, but what we got for h was 1. So x is equal to 1. All right, so here we go. Let's start doing this. So our values are they're pretty regular. We could do, why don't we do this? I mean, we'll just do the regular scale on this. I don't think our numbers were too terribly small for the x, so we'll do our regular scale, which is plus or minus 10. And then let's see what order pairs we already have, and then we'll go from there. So the vertex 1, negative 2, that's our vertex. Our axis of symmetry, that's important to do early, is going to be at x equal to 1. And we got our x-intercepts at approximately negative 0.40 and 2.40. So negative 0.4 will be about here, and then 2.4, so that's 2.4 about here. And this one might be a little bit over. Now notice they're each 1.4 away from our axis of symmetry. And we have our y-intercept. Our y-intercept was at, and I didn't write this in, the y-intercept was at the ordered pair 0, negative 1. So 0, negative 1. Which means we're going to get another pair if you kind of go across, we'll get another ordered pair here. So we actually have 5 ordered pairs. They're kind of close to each other though. So I think I'm going to plug in, one other value, and that'll give us 2 more points. So here we go. If we evaluate, so we're doing extra points. So why don't we do f of three? So that's going to be 3 minus 1, the quantity squared, minus 2. So 3 minus 1 is 2, 2 squared is 4, 4 minus 2 is 2. So we're going to get an ordered pair at 3, so 1, 2, 3, comma 2. Now that's 1, 2 units away from the axis of symmetry, so by symmetry I'll get that ordered pair as well. And I think that's going to be enough. We'll go ahead and connect all these up. Oops. And we've got our parabola. All right. Okay, so if you feel very confident, then you can go ahead and do this next guy, or you can just do it along with me. It's up to you. So here we go. Let's see what we've got. We might want to rewrite this one. This one is equivalent to f of x equals 2 times. Remember that it was x minus something? So if we write x minus negative 2, do you guys see that that's the same as x plus 2? And then here, plus a negative 1. And that's going to give us, remember, our a is the 2. Our h is that negative 2. And our k is the negative 1. And since we're on a new page, I'll write the general form. F of x is equal to a times x minus h, the quantity squared, plus k. So all I did down there is I wrote it so I could match everything up exactly. So first up, we're going to have, we figure out which way it opens, right? So 1, a equals 2, which is greater than 0, so it opens upward. Secondly, we needed to find our vertex. Well, we already identified the components. The vertex, remember, is h comma k. Well, this is equal to negative 2 comma negative 1. Again, this was our a, this was our h, and this was our k. Thirdly, we want to find the intercepts. So the x-intercepts, you set f of x equal to 0 and solve. So 0 equals 2 times x plus 2, the quantity squared, minus 1. So if I add 1 to both sides and divide by 2, I'll get x plus 2, the quantity squared, on the right. Square rooting both sides, we will end up with the square root of 1 is 1, and so we'll end up with x plus 2 is either equal to positive 1 over root 2, or x plus 2 is equal to negative 1 over root 2. Now, we've been rationalizing these things, so we're going to go ahead and do so. And we'll also get that 2 on the other side. So x will be equal to negative 2 plus, when I rationalize, remember you multiply by whatever number will give you a rational number. So in this case it was root 2 over root 2. So we end up with root 2 over 2, or x is negative 2 minus root 2 over 2. So getting one happy fraction and putting it in terms of an ordered pair, we'll end up with, you know, if I multiply the 2 by 2 over 2 in each of them, we end up with negative 4 plus root 2 over 2, comma 0. And we'll get on this one negative 4 minus root 2 all over 2, comma 0. And then I went ahead, and so that we could graph that more easily, I went ahead and got an approximation. So on this one, when we're adding, we end up getting approximately negative 1.3, comma 0. And on the other end, we'll get negative 2.7, comma 0. Okay. The y-intercept, that's our fourth step before we start graphing. The y-intercept. And remember, with the y-intercept, we're evaluating f at 0. So f at 0 will be 2 times 0 plus 2, the quantity squared, minus 1. That will be 7 when you simplify. So our y-intercept will be the ordered pair 0, comma 7. So these numbers, again, I think we can just use our regular scale on this. So we've got x, we've got f at x. This is 10, negative 10, 10, negative 10. So here we go. First step, let's graph our vertex. And that's at negative 2, negative 1. That was our vertex. That's very important. And our axis of symmetry, remember, is going to be the vertical line x equals negative 2. So this guy is axis of symmetry, and it was the line x equals negative 2. And then let's graph some of our other ordered pairs. Our x-intercepts, we've got one at negative 1.3, comma 0. So there's negative 1, probably about here. And then negative 2.7, so 1, 2.7 about here. And then we had our y-intercept. And so our y-intercept is going to be at 0, 7. 1, 2, 3, 4, 5, 6, 7. So this is 2 units. 2 units to the right of the axis of symmetry. So if I count 2 more units, I'll get another ordered pair by symmetry. And that'll be enough to graph it. And we're all set. Okay. Now, sometimes you don't have that format. A lot of times a person, would need to, a lot of times a person would need to actually complete the square to get it in that format. So you learn both of these techniques, and what I would do is just, see what format you're given your equation, your quadratic function, and then decide which technique you should use. So if you've given one that's been multiplied out, it's not in factored form. I mean, the other one was sort of in factored form. This is in standard form. What happens is the vertex, it turns out, will be negative b over 2a, comma, the function evaluated at negative b over 2a. The x-coordinate is the negative b over 2a, and the y-coordinate is found by substituting, that x-coordinate that you found up there, the negative b over 2a, into the parabola's equation and evaluating. So it's just the corresponding y-coordinate that that you get when you plug in that negative b over 2a. Actually, I'll just write this particular value of x. All right. So here we go. Find the coordinates of the vertex. So let's just let's just see what we got. In this one, do you see that a in this format is 3, good. B is negative 12, just like when we use the quadratic formula. And C is positive 1. So the x-coordinate is negative b over 2a, which is negative 12 over 2 times 3. So we'll just leave it like that. So then we'll get, when we simplify, we'll get a positive 2. Minus a minus is positive, and then 12 divided by 6 is 2. So then here, the y-coordinate is going to be the function evaluated at whatever you found. In this case, it was 2. So then you get 3 times 2 squared minus 12 times 2 plus 1. So this will be 12 minus 24 plus 1, which is negative 11. So your vertex is 2, negative 11. So you just need to do a little bit of computation for that one. Okay, go ahead and pause the movie, and you guys try part B and C, right? And see how you do. Good luck. Okay, let's see how you did. What's our A, B, and C on this guy? Our A is negative 2, good. B is 7, and C is negative 4. So our x-coordinate of the vertex will be negative b over 2a, which will be negative 7 over 2 times negative 2. This is, let's see, positive 7/4. The y-coordinate of the vertex will be the function evaluated at 7/4, which is negative 2 times 7/4 squared plus 7 times 7/4 minus 4. That's going to be -2 times 49/16 plus 49/4 minus 4. We can simplify a little bit. The LCD is 8, so we're going to end up with all of this will be over 8. We'll have -49 because that one already had the LCD. This one we need to multiply by 2 over 2, and the 4 we need to multiply by 8 over 8. So we'll end up with 98 for the middle fraction, and then minus 32. So we'll end up with 17/8. So our vertex will be, for this guy, the vertex is the ordered pair 7/4, comma 17/8. Okay. See, I was kind of suckering you in here. Do you guys see that you don't need to multiply it all out and then construct it this way? This was given to us in the form of, of this format. F of x is a times x minus h, the quantity squared, plus k. So I'm going to do it the easy way. That's my h. This guy is my a. And then this guy is my k. So the vertex will be at negative or positive 2, my bad, it's the number that comes after the minus, comma 12. All right. Okay, so graphing these guys. Same kind of deal. The main difference is, instead of finding, you've been given the equation in the other format, so you got to use the negative b over 2a business to find your vertex. So determine whether the parabola opens upward or downward. And again, you can use the same, downward. The same idea. If a is greater than 0, the parabola opens upward, and if a is less than 0, the parabola opens downward. Determine the vertex of the parabola. The vertex is the ordered pair, negative b over 2a. The function evaluated at negative b over 2a. Find any x-intercepts by solving f at x is 0, and then find the y-intercepts, or y-intercept, you only get one of them with this type of graph, by computing f evaluated at 0. And then plot the intercepts, the vertex, and additional points as necessary. Connect the points with a smooth curve that is shaped like a bowl or an inverted bowl. Alrighty, so here we go. So, A is 1, B is -2, C is -15. So first step, A is 1, which is greater than 0. So that means it opens, good, upward. 2, finding our vertex, right? So the x-coordinate is found by finding negative b over 2a, which is negative 2 over 2 times 1. I just got that from what we had up there. So this is going to end up being positive 1. The y-coordinate we find by evaluating the function at 1. So that's going to be 1 squared minus 2 times 1 minus 15, which will be negative 16. All right, 3. X-intercepts. I'm going to just go ahead and it's up to you. I mean, you can factor it. You can use the quadratic formula. Let's just go ahead and we'll use our quadratic formula since we have it laid out. So x is equal to the opposite of b, which is negative 2, plus or minus the square root of b squared minus 4 times a times c, all over 2 times a. So this will give us x is positive 2 plus or minus, let's see that radical. We're going to get 4 minus a minus 60 rather. So that'll be a positive 64 all over 2. So x will be, do you guys see that root 64 is 8? So we'll get 2 minus 8 over 2, or x is 2 plus 8 over 2. So x will be, that would be negative 6 over 2 is negative 3, or x is 5. So our intercepts will be at negative 3, 0. Our x-intercepts will be at negative 3, 0. And we'll have another one at 5, 0. Fourth step, finding our y-intercept. Remember, the y-intercept is evaluating f at 0. So the x-intercepts, we had set f of x equal to 0. The y-intercept, we find f when x is 0. So f at 0, it's kind of cool on this one. Do you see that you're going to be left with c all the time when you're in this format, because the other ones have x's in there? So when you evaluate the function at 0, you'll get negative 15. So here, do you guys see that we've got, we need to extend our y-axis. So I'm going to have the upper value, I'm going to count by 2's on the y-axis, but I'll leave the x-axis as counting by 1's. So just be careful when you're graphing. So here we go. Let's graph all the stuff we have. Our vertex, oh, I never wrote out what it was. So the vertex is at 1, negative 16. We found that out by doing the work. So 1, negative 16, so that'd be here. We're going to open upward. And then we have our intercepts, 1, 2, 3, 0. And then 1, 2, 3, 4, 5, 0. Our y-intercept was at negative 0, negative 15. So that'll be here. It'll be halfway in between because we were counting by 2's, which means I'm going to get a bonus ordered pair. I'm 1 unit from axis of symmetry, so I'm going to get my bonus right here using symmetry. Remember that the axis of symmetry will be at x equal to 1. So that is our axis of symmetry. And then graphing it'll be something like this. And this was our axis of symmetry. Oh, and you know what we forgot to do is identify the range. So that axis of symmetry was x equal to 1 in this case. And we'll go back and identify the range on all our graphs. So the range, so again, you look at the smallest value. So the smallest value we have, it's included, and you see it's down at -16. And then the graph goes up without bounds. So that's our range. The domain for parabolas is easy. It's always the whole line, -infinity to infinity. So let's identify, we had a couple graphs. So the range, what's the range of this graph? Good. It would be from -2 to infinity, because the lowest value is -2 and it's included, and then it increases without bound, because these have all opened upward if I remember correctly, so they all have minimum values. So this one, the range will be, good, the lowest of the low is -1, and then it increases without bound. Okay, and then we have one more graph to do, I believe. So if you want to go ahead and pause the movie and try it on your own, feel free. Just a little hint, you might want to rewrite this guy as -x² minus 4x plus 5, so you can identify your A, B, and C more easily. Okay, let's see how you did. A is -1, B is -4, and C is 5. So step 1, A is -1. That one's less than 0, so it opens, good, downward. Secondly, finding our vertex. So the x-coordinate of the vertex will be at -b over 2a, which is -4 over 2 times -1. I've got 3 negatives there, so I end up with a -2. The y-coordinate is the function evaluated at the x value we got, which was -2. So that'll be, I'll just use the original, 5 minus 4 times -2 minus -2 squared. So that's going to be 5 plus 8 minus 4, which will be at +9. So our vertex is at the ordered pair -2, 9. Okay, thirdly, finding our x-intercepts. And these, remember, occur when you set f at x equal to 0. So we get 0 is equal to -x² minus 4x's plus 5. Whoops, I didn't want to do it all in red, sorry. So coming up here, again, I'm just going to go ahead and use the quadratic formula. So x is equal to the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So x will be 4 plus or minus. We'll get 16 plus 20, which is 36. So we'll have another perfect square there. So x will be 4 minus 6 over negative 2, or x will be 4 plus 6 over negative 2. So 4 minus 6 is negative 2 over negative 2 is positive 1, or x will be negative 5. So then our x-intercepts will be at 1, 0 and at negative 5, 0. The y-intercept occurs when we evaluate the function at x equal to 0. So remember, we'll just get our c, which was 5. So the y-intercept will be at the ordered pair 0, 5. Okay, so we don't have any huge numbers here, or very, very small numbers. So let's just use our regular scale. And start plotting our points. This is our 5th step. So our vertex was at negative 2, 9. So that means our axis of symmetry will be good at the line x equals negative 2. That's our axis of symmetry. Okay, so then graphing our other values, we've got intercepts. Let's see, 1, 0, and then we had one at negative 5, 0. Our y-intercept was at 0, positive 5. So that means we'll get another ordered pair where? Good, we're 2 away. So at the same y value, we'll go 1, 2 here, and we get a bonus point. And I think that's good enough for us to do our graph. Something like that. It's a little jagged. I want to smooth it out a little more. Okay, so you know what? I'm gonna redo the curve. I really don't like it when it's looking like a V. You know, it's supposed to be a smooth curve. So let's do little. There we go. I think that's a little bit better. Okay, so now we need to figure out our range. Oh, and we'll label this was our vertex. And then our range is going to be, let's see, this time it's got a maximum value. So do you see it goes from now minus infinity all the way to, good, all the way to 9. Oh, and we include 9 because that's the highest y value, and there's no bound on the below y values. All right, so next up we go into minimum and maximum for quadratic functions. All right, so this is special for quadratic functions. So consider f of x equals ax squared plus bx plus c if a is greater than 0, then f has a minimum that occurs at x equals negative b over 2a. This minimum value is the function evaluated at negative b over 2a. So it's that y-coordinate. So if you're asked where it's located, you give the whole ordered pair of the vertex. So the input at negative b over 2a yields a minimum at f at negative b over 2a. Now, if a is less than 0, then f has a maximum because it opens downwards, so it's going to have a maximum that occurs again at x equal to negative b over 2a. This maximum value again is the function evaluated at negative b over 2a. In each case, the value of x gives the location of the minimum or maximum value. The value of y, or f at negative b over 2a, gives the actual minimum or maximum value. So you just need to read the wording very carefully. Okay, so here we go. Here's the application problems associated with this type of thing. So, you get started like you always do. First step, you do some sort of analysis, name your variables. So we have, among all pairs of numbers whose sum is 20, find a pair whose product is as large as possible. What is the maximum product? So the trick to these is you're given two sets of information. You're given the quantity that you're wanting to optimize, which is a generic way of saying either maximize or minimize. And then you're given secondary information, which allows you to isolate one variable in terms of the other. So here we go. Why don't we let x be the first number, and we can let y be, let's not use y. I don't want you to get confused. Why don't we just use z be the second number? Now, let's see. Another key piece of information is we are looking for the maximum product. So the maximum product with these numbers, we can say P equals X times Z. We also have this other information. What information do we have? Good, that the pair of numbers sum to 20. So X plus Z is 20. So let's put that all together. And by the way, this would allow us, if we isolated Z in terms of X, Z is 20 minus X. So here we go. If we want to translate this stuff, what we end up with is P in terms of X alone. This is the trick. Well, first we'll just say P. P, remember, was equal to X times Z. Now, if we want to write P just as a function of X, we've got X times, what was Z? Good, Z was 20 minus X. So I took Z is 20 minus X. That's from over here. All right? Okay, so now this, of course, we want to write it in a format that's useful to us. So do you see that this is 20x minus x squared, which, if we write it in the form we're used to for a quadratic, negative x squared plus 20x's. So now we have something quadratic in form. They're asking us what's the maximum product. So we find the vertex, right? So we're going to find the, I'll just say vertex. And you know what? And the numbers. We'll find everything. Okay. So here we go. The x-coordinate of the vertex will give me one of the dimensions. And remember, that is negative b over 2a, which is negative, my b is 20, over 2 times negative 1. So that's going to be positive 10. So I have my first number is 10. Now the max product, all right, so the maximum of this product equation is going to be at the function p evaluated at 10, which is negative 10 squared plus 20 times 10, which will give me negative 100 plus 200, which is 100. Now what else do we need to find? Good, we need to find that other value z. So remember that z was equal to 20 minus x. So we found that x was 10. So z is equal to 20 minus 10. So z is also 10. So let's just write our conclusion. The first number is 10. The second number is 10. And the maximum product is 100. Okay? All right. So one more problem for this section, and then we'll be all done for today. So this one, it's really kind of similar. You've got 200 feet of fencing, which is a linear measure, and you need to enclose a rectangular plot that borders on a river. If you do not fence the side along the river, so you're using the river as a fence for that side, find the length and width of the plot that will maximize the area, and then find the largest area that can be enclosed. So here we go. Here's our little analysis. So we have our river. Okay, it doesn't need to be that long. We have our river, and then we want to, fence this. So we have, it's a rectangular plot. Okay, so if we call this the width and this the length, let's see what we know about it. Okay, we want to maximize the area. So why don't we name our function a? So a is equal to length times width. It's okay that the river's the border. You still have a rectangular region. Now, what other information do we have? We know that all the black is fencing. So we also know that the two W's plus the L has to be what? Good, it has to be 200. So I'm going to go ahead and isolate the L. That's the easiest one to isolate. We get 200 minus 2W. Okay, so now if we go ahead and translate this, again, we've got this area was equal to length times width. Area in terms of width alone, since we had isolated L, is going to be that 200 minus 2W is in for L, and then times W. So I had this for L, and this is what I plugged in for L. By the way, when you're in calculus, you're going to be using this a lot. So now I'm going to go ahead and do the W times the negative 2W first to get it as negative 2W squared, and then I'll have plus 200 W's. So I did this guy first and then that guy. All right, so now what do we need to do? We need to, find the vertex, and from that we'll find the dimensions. Okay, so the or I guess in this case it'll be the W coordinate for the vertex because we didn't name it X. So this will be, again, it's the same, negative B over 2A, which is negative 200 over 2 times negative 2, which is going to be positive 50. And then the maximum, which would be the maximum area, I'll write that in, is going to be the area evaluated when the width is 50. So that will be negative 2 times 50 squared plus 200 times 50. This will be negative 2 times 2500 plus 10,000, which is negative 5,000 plus 10,000, which is 5,000. And so the length, remember, was 200 minus 2 times W. We found that the W coordinate was 50. That yields this maximum area. So L will be 200 minus 2 times 50. So L will be 200 minus 100, which is 100. So let's put it all into our conclusion. The length and width that maximize the area are 100 feet and 50 feet, because I said length first. I'll just say respectively. And the maximum area is 5,000 square feet. And we are done for today. That was a long one. Have a great evening. Make sure you do at least some of the problem set afterwards, and you'll be hearing from me shortly.